All right, so in the last video, I introduced you the term free energy, and I also gave you the Gibbs free energy relationship that the delta G is equal to delta H minus T delta S. And if you are carrying out your calculations at standard state conditions, that means solids, liquids, and gases are in their pure form. If there is pressure associated, it will be 1 atm. Solutes will be at 1 molar concentration. The temperature will be 25 degrees Celsius or 298 Kelvin. Those are standard state conditions. And in that sense, if we are measuring our free energy change, then we call it a standard free energy change. And we look at it as delta G naught. So this is 0 basically signifies that everything is run in their standard state. And so the Gibbs free energy relationship can be written in standard state as delta G naught or delta G zero, as it's called, to be equal to delta H zero minus T delta S zero. Now, two things that I want to say here is, first of all, if you had to determine the delta G zero for a certain reaction, then you will need the delta H for the reaction and the T delta S for the reaction as well. And so hopefully you can recall that the enthalpy can be figured out as the heat of reaction by using the delta HF, the heat of formation reactions, for a balanced equation. We can use that, and earlier in the previous video we saw that we would be able to use the absolute entropies for the case of calculating the delta S naught. And so if you have the final product minus reactant, if you have those numbers, you should be able to calculate the delta G zero, and we'll take a look at some of those examples. And then there is a second method where we will use the tabulated values of the free energy of formation to calculate the delta G naught reaction directly. So we won't be needing the delta H and delta S values in that case. We would be using just basically delta H, or I'm sorry, delta G products minus delta G reactants, and we are going to take a look at that as well. And then there'll be a third method in which we will determine the free energy change for a stepwise reaction, kind of similar to the Hess law that we discussed in Gen Chem 1. So let's take a look at all of these one at a time. The first one is consider the thermal decomposition of calcium carbonate, and it's decomposing to give you CaO and CO2. Delta H naught is given to be 178, delta S naught is given to be 160.4. You have to do several things. Calculate the standard free energy change for this reaction. That means you have to determine delta G naught. So hopefully you can see that all you have to do is delta H minus T delta S. Values are provided, temperature is provided, it's basically plug and chug. And then they ask you, will a mixture of solid CaCO3 the way it is that going to react spontaneously? And if not, then you have to estimate the temperature at which it is going to happen. So we are going to take a look at that as well. So let's do one thing at a time. The first thing you should do is really convert the kilo into joules. And so hopefully you can see that that will be done by multiplying this by 1,000. And that will give you a value of 178,300. Minus temperature is 25. That means 298 Kelvin. So 298 times 160.4, and so 298 times 160.4 is 477. This number is 47799.2, and this number is being subtracted from 178,300. So 178,300, from that subtract 47799.2, and that gives you a value. It's going to be a positive value, 13050 0.8 joules. And realize that this is a positive value. That means this is not going to be a spontaneous reaction. So we will say that the answer to B is no, and the reason for that is because the delta G is positive. And so when they ask you at what temperature would this become spontaneous, realize since both of these are positive values, and I told you in the last video, positive, positive, and high T, hit. Positive, positive is hit, is another way to remember this. So if both delta H and delta S have the same sign, that means higher temperature is going to facilitate this. What that would mean is you will set up the delta G is equal to 0. So delta H minus T delta S is going to be equal to 0. Or you can say that 178300 divided by 160.4 should give you the temperature, and that value is going to come down to be 178300. Divide that number by 160.4, so that's 1111.5 or zero point 0.6 rather, and this will be in Kelvin. So if you had to kind of ballpark a guess estimate or be accurate about it, 838.5, that means that you really have to heat the calcium carbonate, and that will give you the CaO and CO2. And that makes sense because if this decarboxylation process would be spontaneous, then the Taj Mahal, which has been staying, it was built in the 1400, 1500 century. It's been there for about 500, 600 years. There's a whole boatload of buildings that were made in the medieval period in Italy and across Europe. So marble would not be able to be used as a manufacturing material if this decarboxylation process would occur at room temperature. Just an FYI, again, marble is CaCO3. Just a reminder for that. Hopefully this is clear. Let's forward. Like I said, another method. So the first method that we used to determine the delta G was utilizing the delta H and delta S. And if initial and final values are given, then you will have to figure that out. But if it is given for the reaction, then of course you use it directly the way we did in the previous example. The second method is to utilize the delta G formation. So if a table of delta G formation numbers are already provided, you would be able to use those directly, and then just carry out the summation of all the products put together, all the reactants put together, and then just go product minus reactant. So if one had to define the free energy change for formation of just 1 mole of the substance in its standard state, which would mean that it is in its most stable form and it has been formed from its constituent elements, you would call it a delta GF. That's how we define the enthalpy of reaction as well, that only 1 mole has to be formed, and it has to be formed from the constituent elements, and everything has to be present in their standard steady state. And that's exactly how we do that for the free energy of formation as well. The one thing that I would say here is that if you see positive delta GFs, that basically means that particular material is not going to be very stable, because that's not a spontaneous process. On the other hand, if you do have a negative value, then that tells you that those species are stable and they're not going to decompose into their constituent materials under the standard state condition. Again, the positive delta GF is thermodynamically unstable, so it's a little bit redundant to try to use those materials, because that decomposition reaction is going to take place pretty easily. And so it's no point to try to synthesize a material because it's going to anyways degrade into its constituents very readily. So again, if you had the delta GFs for all of your products and all of the reactants, and you had a balanced equation, let's say A moles of A react with B moles of B, giving you C moles of C and D of D, then you consolidate all the products together. So what you would do is you would bring in the delta G formation for C and D, you would multiply it by the number of moles, by the respective number of moles. So that would consolidate all the products here. You would do the same thing for the reactants. So the free energy of formation will be multiplied by the number of moles of A, and you would do the same thing for B. That would consolidate essentially the reactants, and then you just go products minus reactants, and that gives you the delta G0 for the reaction, much the same way as we did for the heat of reaction in Gen Chem 1, and we saw that earlier for the entropy, the absolute entropy as well, earlier in a previous screencast. All right, let's see if we can apply this concept. So now we are using the second method of evaluation of determination of the delta G reaction. The reaction here is that calcium carbide is being treated with water, gives you ethine and COH whole twice. The question is calculate the standard free energy change for the reaction. And then they ask you, might this reaction be used for synthesis? So basically, they're asking, in other words, is this reaction spontaneous? Is this reaction spontaneous? Because you only want to use something which has a negative delta G, or a spontaneous reaction, if you want to use it for an industrial scale, for instance. The delta GFs for the reactants as well as the products are provided. So we're just going to set up the system. We would say delta G0 reaction is going to, of course, first of all, it's a good idea to verify that it's a balanced equation, but looks like it is. We have 2 carbons here, 2 carbons for the carbide. We have 2 hydrogens and 2 hydrogens. 2 times 2 is 4. 2 oxygens taken care of, 1 calcium. We're good to go. Let's consolidate the products first. So C2H2, where's my, I have 1 mole of that only, so 1 times, and I'm just going to write the 1 times just so that you start getting used to putting, the multiplying the number of moles. We have only 1 mole of the calcium hydroxide as well, so 1 times negative 898.6, and from that, we are going to subtract out CaC2. We have 1 mole for that. That's negative 64.8. And we have 2 moles of water. So 2 times negative 237.2. And then just solve. So we have here, we have negative 898.6, and we have a positive 209.2, so they must be subtracted. This number will come out to be negative 689.4. From that, we are subtracting out 64.8, and we have a negative 237. So that comes out to be minus 539.2. And so when you work the math out, it gives you negative 150.2 and kilojoules. That's your answer. That's your delta G. And since it's a negative value, that tells you something. That tells you that this particular species is going to be formed by this method because you have a spontaneous reaction. And this is actually true. This is an industrially relevant method of synthesis of acetylene. Those of you who have to take organic 1 and 2, we will actually discuss this reaction in organic 1. All right, let's go forward. Now, one thing that I would like to say here is in any reaction, if you have like H2 or O2, which is in its elemental form, then the delta GF is going to be 0, because that's how nature intended to prepare it. So by definition, elements will have a standard free energy of formation of 0. And most compounds, you would see that they would have a negative standard free energy of formation, and that basically tells you that those compounds spontaneously form from their elements in their standard states. And if there is a compound which has a positive free energy of formation, that basically tells you that it's not a spontaneous reaction. Such compounds would be more, they'll be rarer, they'll be less common, but just a couple key points that you should kind of keep an eye on. All right, let's take a look at the third method of calculation of the delta G0 reaction. So delta G0 reaction can also be calculated for a stepwise reaction. And this is the one that I told you, which was kind of similar for the way we handled Hess law. It's similar to that. Realize that since enthalpy is a state function, entropy is a state function as well, just the same way as the heat of reaction can be calculated for a stepwise reaction as the sum of changes in enthalpy, which was basically what Hess law was, we would be able to apply that for the free energy as well. What that means is that as long as you're able to follow certain rules, you would be able to figure out the delta G reaction for that particular overall chemical reaction. So for instance, if a chemical equation, if the equation is multiplied by a number, by some factor, then you should do that for the delta G reaction as well. Delta G must be multiplied by the same factor. That's the first rule. If you reverse an equation, so if you reverse an equation, that basically means that you are multiplying it by -1. That would mean that the delta G reaction is going to switch signs. It would change sign. And then a chemical reaction or a chemical equation which can be expressed as sum of some steps. So if you're adding equations, then you must carry out the same mathematical operator, operator for the delta G as well, the delta G reaction as well. So if we follow that, hopefully we should be able to carry out a math problem based off of that. So let's try to apply this to a problem here. You're given, the question is find delta G0 reaction. The reaction in question is that you are forming C3H8 from the elements carbon and hydrogen, and some data is provided to you. You have been given that C3H8 goes through combustion to give you CO and water, and there's a delta G0 reaction for that. And then carbon burns an oxygen to give CO2, and 2H2 and O2 gives you 2H2O. So those are that's some data that is provided to you. Now, a couple of things here. First of all, notice that in your final reaction, and I'm going to use the same strategy we learned for Hess law. For my given reaction for which I have to determine the delta G naught reaction, the aim is basically to manipulate these three reactions in such a manner that it starts reflecting the given reaction. So first things first, I have C3H8 on the product side and here I have it on the reactant side. So probably I should invert it. So if I invert it, that means I need to write down the products on the reactant side, reactants on the product side. In other words, I am multiplying that equation by -1. That means that the delta G naught for that reaction should be written with a positive sign, since right now it's given to be a negative sign. I need 3 carbons. The given reaction is for only 1 carbon. So the second equation that you have, so I did 1 times -1. The second equation that you have, I think I should multiply it by 3. And the reason for that is so it starts showing me 3 carbons. So 3 carbons plus 3 oxygens will give you 3 CO2. And the delta G for that reaction is going to be negative 394.4 times 3, which is going to give you, on my calculator, 1183 kilojoules. And the way I got that was negative 394.4 times 3 is what I did. All right. The next thing you should think about is that you have 4H2, and right now the given reaction, that reaction is for 2 H2s. So I'm going to multiply the third equation by 2 so that it shows me 4H2, 2 O2s, and 4 H2Os. And the delta G naught for that will be negative 457.1 times 2, which is going to give me negative 914.2 kilojoules. And now I'm going to simply add the new manipulated equations. And when you add, hopefully you can see that the CO on left side is going to, this is CO2 actually, my bad. The CO2 is going to cancel off with the CO2. The 4H2O will cancel off with the 4H2O. The 5 oxygens, 3 plus 2, 5 oxygens will cancel. So you are seeing 3 carbons plus 4 hydrogens giving you C3H8. And since we have added, all I'm going to do is add the delta G's values as well. So that's going to look like 2074 minus 1183 minus 914.2, and that gives you negative 23 kilojoules. And so the reaction is spontaneous the way it is written. Now, I want to just very quickly remind you of the fact, why is free energy free? So recall that the free energy basically means that that's the amount of energy that is available to do any usable work. For example, in case of an automobile, we use the energy released by the combustion of gasoline to move the car, to honk, to use the headlights, all of that. And of course, the engine gets heated up as well. So the change in free energy of the chemical reaction represents the maximum amount of energy available or which is free to do the work, provided the delta G is negative. However, there would be reactions in which the amount of free energy would be less than the change in enthalpy for the reaction. So for example, just to give you a flavor, when carbon reacts with hydrogen and gives you methane, which is a gas, hydrogen is a gas as well, and you need 2 of those, and carbon is a solid. Now the delta H for this reaction is negative 74.6 kilojoules. Delta S for this reaction is negative 80.8 joules per Kelvin. And delta G for this reaction is negative 50.5 kilojoules. What does this data tell you? This reaction occurring at 298 Kelvin. The reaction is exothermic clearly. It gives off 74.6 kilojoules of heat energy. What that tells you is that even though what is given off is 74.6, only about 50.5 is available for the useful work. Why would that be? Where did the rest of it go? Well, realize that the change in entropy also is a negative number, but this is for the system, of course. This is for the system, and that would mean that and the reaction is spontaneous because the delta G is with a negative sign. That would mean that the delta S universe must have been a positive value. That would mean that if delta S system is negative and delta S universe is positive, that means the delta S surrounding should be positive too, and that makes sense because the surrounding comes from the system, the delta H system, and this is an exothermic process. We learned this. I spent a lot of time explaining to you that for an exothermic process, the delta S surrounding is going to go with a positive sign, and if that goes with a positive sign, it is going to make the change of the change in entropy of the universe to be a positive number as well. And that would mean that the amount of energy available to do the work is what is left after accounting for that heat that would be lost to the surroundings. So it's because of that entropy factor, the loss that occurs, the dispersal that occurs, that the delta G reduces. Now, one thing that I would say that it is not necessary that all reactions that you run are always going to occur at standard state conditions. Yes, we see that standard state conditions are sort of more stable, but it's not necessary that all measurements are done at temperatures and pressures. And so if the temperature and pressure is going to be a different value, so if it's a non-standard state, how can you relate the standard state to determine the delta G? In that event, we can calculate the free energy change of a reaction under a non-standard condition as delta G for the reaction to be equal to delta G naught plus RT ln Q. And of course, this is done for the reaction. So if you had an idea about the reaction quotient, so recall the QC or QP from equilibrium that we discussed. Reaction quotient is that snapshot which is infinitesimally small. Temperature is, of course, the T in kelvins, and R is a gas constant which has a specific value of 8.314 joules per Kelvin per mole. So those are the values that we are going to use, but QP or QC, as the case may be, would give you an idea about which direction the equilibrium would be. So you should be able to calculate that, and you should be able to plug the numbers in to get your answer. Now, for a basic reaction where water is going from a liquid state to water in the gaseous state, the delta G naught for this reaction is 8.59 kilojoules per mole. So that's the value for this system. And if we had to use this liquid vapor water equilibrium at different conditions, then we would want to use this given equation. We would want to use that for the system. Now realize that for the law of mass action, if you try to use that for this phase change equilibrium, you would say that the QP or Q rather, is going to be dependent on just the pressure of water for the gas form. The H2 and liquid is not going to participate. And since if you were to make the measurement at standard conditions, then that pressure of water is going to be 1 atm, and so essentially natural log of 1 is going to be 0, and so in that event the delta G and the delta G0 are going to be exactly the same. So you can perhaps envision that if you were to kind of plot out the free energy, the G, let's just call it G. If you were to plot out free energy against the pressure of H2O, okay? Now the free energy for a spontaneous process means that the delta G is going to be negative, and we know that for an equilibrium it's going to hit the 0 mark. So let's say that's the 0, and then it's going to rise up again. So this is the point where essentially the delta G flips. So realize that in this case, delta G for standard condition is going to be equal to the delta G reaction. So if you were to plot between the 0 atmosphere to the 1 atmosphere, at the minimum is where the equilibrium would be. This part of the curve is going to give you the delta G, which will be negative signs, whereas the other part is going to give you the delta G with the positive signs. So what that means is that if you go back to your equation, delta G is equal to G0 plus RT ln Q, and if your reaction mixture, the RM stands for reaction mixture, if your reaction mixture contains mainly reactants, that means the value of Q is less than 1, and you're going in the forward direction. That means the RT ln Q is going to be less than 0, and if this part is going to be less than 0, then the delta G is going to be less than 0 as well. Alternatively, if the reaction material is mostly products, and if Q is really large, then in that event you can expect that the delta G is going to be greater than 0. That means at equilibrium the delta G is going to be equal to 0, and what that means is that delta G naught plus RT ln Q, this is at equilibrium, or is going to be equal to 0, or that delta G0 is equal to negative RT ln Q. Now also realize that Q tends to, it becomes K at equilibrium, so your relationship will start looking like negative RT ln K is going to be equal to G0. So you should be able to calculate the delta G0 for a reaction, again standard state, provided you have some idea about the equilibrium constant. And this idea will become very handy in chapter 19 when we talk about electrochemistry. But at equilibrium, delta G, without the naught, delta G is going to be equal to 0. So to give you an idea, again, if you have reactions, and perhaps I'll just add another, if you have reactions where the K is much less than 1, that means the natural log of K is a negative value as well, and so the delta G0 is going to be a positive value. And so under standard conditions, that means Q being equal to 1, the reaction will be spontaneous in the reverse direction, and reverse reaction is going to be more spontaneous because if forward has a positive delta G, that means reverse will have a negative delta G, and so your your graph for the free energy against the extent of reaction, it's going to look a little bit more on the left hand side, signifying that the K value is less than 1. On the other hand, if the K value is greater than 1, it's going to look a little bit on the in the opposite direction towards the product side. And when K is exactly equal to 1, it's completely balanced in that case. So that's at equilibrium. That's K equals 1. So again, to illustrate, delta G reaction, which is a positive reaction, that means the reverse is going to be the spontaneous reaction. If delta G is negative, that means your forward reaction is spontaneous. And if it is equal to 1, that means that ln k is going to be equal to 0, and that means that delta G0 is going to be equal to 0, and that's an equilibrium standard state conditions. Okay. Let's see. The next question is, which of the following can always predict the spontaneity of a reaction? Enthalpy? Not really. Delta S? No. Because it's only the delta S universe, not system or surroundings. So what is the most foolproof way of doing that? Look at the delta G. That number has to be a negative value for a spontaneous reaction. Hopefully that point has been drilled across. Negative delta G. Okay, we have seen this before, the effects of delta H, delta S, and temperature on delta G, and I gave you that if you have a negative delta H but a positive delta S, then it's always going to be spontaneous. If both of those are negative, or if both of those are positive, then the effect of temperature is seen. Effect of temperature is there, and so remember, positive is a hit. So high temperature, high temperature, high temperature. And if we have an endothermic reaction and the entropy is going to be a negative value, then it's going to be never a spontaneous reaction. All right, given the data below, calculate the temperature at which the reaction becomes spontaneous. So again, the way you would work this out is you would basically set the delta G naught to be equal to 0, and so 92,000, and I just want to keep the units intact, is going to be equal to T delta S, so T times negative 199, negative and negative will cancel off. 92,000 divided by 199 is going to be equal to, let's see, 92000 by 199 is 462.3 Kelvin, and that's your answer. Any temperature, since both of these are negative values, that means low temperature is going to facilitate spontaneity. So any temperature less than temperatures less than 462.3 will give you a spontaneous reaction. Okay, now anytime the delta G is negative, that means spontaneous reactions are also called as exergonic reactions, especially important for biochemical and organic reactions, this term. Likewise, delta G of positive, which is greater than 0, those will be non-spontaneous reactions, also called as endergonic reactions. So much the same way as delta H was exothermic and delta H with a positive value was endothermic, we use the word endergonic and exergonic. The G is for the delta G that gives free energy. So the question might occur, well, the entire breakdown of glucose, all of that actually occurs on its own. So if you look at the breakdown of glucose and the generation of energy, it's a stepwise series where glucose goes through glycolysis through a series of reactions to convert the glucose into the pyruvate, and that pyruvate then enters the TCA cycle, and ultimately the phosphorylation reaction takes place at a wide variety of steps during all those three steps of respiration, cellular respiration. So then why is it that we are able to, generate energy, and all of this occurs sort of on its own? And the answer to that is that the main hydrolysis of ATP to ADP, which is what provides the energy for the sustenance of this reaction, that is an exergonic reaction. That means those will have a negative delta G. That means all of those will be spontaneous reaction. That means the entire cellular respiration sustains itself. It finds the energy for itself. You don't have to actually eat food and sit on a stove to be able to, burn up that food. Essentially, it occurs on its own. And that's the key thing in this case. Now, the last thing that I want to leave you with is the temperature dependence. Temperature dependence of the equilibrium constant, and we are going to revisit this idea later on too, but we just saw that delta G0 is negative RT ln K, and we also saw that delta G0 is negative delta H0 minus T delta S0. So equating, both of these equations, one can say that negative RT ln K is going to be equal to delta H0 minus T delta S0. So if I divide both the sides by negative RT, I can say that natural log of K should be equal to delta H over RT plus delta S over R, and you can keep the negative sign, whichever way you wanna. You can keep the negative sign with K or with delta H, doesn't matter. But realize that this is of the format of y is equal to mx plus b. So if you have many temperatures and you are measuring equilibrium constants, you can essentially get the natural log of K from there. So if you plot basically natural log of K against 1 over T, it's going to give you a straight line, the slope of which is going to give you delta H0 over R, and the intercept is going to give you delta S over R. So since R is a gas constant, has a specific value, you would be able to determine the delta H and the delta S from it in a graphical sense as well. So hopefully you can see, based on what we have done in the past, you can express this in a 2-point format also, that natural log of K2 over K1, these are equilibrium constants, of course, is going to be equal to delta H naught reaction over R will be common, and essentially 1 over T2 minus 1 over T1. The delta S is going to cancel off itself. So that's a 2-point version of this equation, 2-point reaction. Okay, that finishes thermodynamics. All right, let's solve the last problem. The question is, you have to determine the equilibrium constant. So you have to calculate K. Given that N2O4 gives you 2NO2, the heat of formations is provided. So realize you can calculate delta G0 reaction for this system. Of course, delta H and S is not provided, but since you have the rest of the information, you can say 2 times 51.3, that caters for all the products, minus 99.8, that caters for the reactants, and that will give you the overall delta G for this system. So delta G came out to be a positive value. it came out to be a positive value. Now, since you know that delta G is also equal to negative RT ln K, this number is 2.8, negative 8.314, temperature is 298, ln K, and then just solve for natural log of K. So ln K comes out to be negative 1.13, and so K is going to be e to the power of negative 1.13, which is showing as 0.32. That's my answer.